Now we have our next speaker, Sir Gail Forget. He currently works as a researcher at Massachusetts Institute of Technology and PI or co-PI of projects funded by NASA, NOAA, AREA, and MIT Portugal program. His research group is focused on ocean sciences and climatology. To this end, he has developed a series of Julia packages such as mesharray.jl, climatemodels.jl, mitgcm.jl, and driftlers.jl, oceanrobots.jl. I welcome Gail Forget, sir.
Great. So let me pause the movie for a second. I'll get back to this. So in this presentation, really, I'm mostly going to set the stage for George, who is going to be doing the presentation of the work that is started. But I wanted to bring up sort of the context and the goals of this project that we got funded together. Oh, I need to play. So the project that I'm talking about has to do with combining model and observations in the sort of ways that we've already talked about in this session and conference. Specifically, we're aiming to look at two regions of the global ocean, the Azores and the tropical Pacific. It's a project with folks that are here, most of them, Adriana, George, and Jao, and then with Jose Silva as well. We are very thankful and grateful for this opportunity that was provided to us by the MIT Portugal organization program that has funded the project 6 months ago. And so this is a 2-year project that we have, and that's going to allow us to really explore some fascinating questions. The summary of the project is here. In essence, we're going to be bringing the models from the MIT side, and by this I mean MIT GCM as well as Oceananigans and other things, and bring them to the applications that are going to be taking place here, and in collaboration with our colleagues in Portugal, focusing on internal waves and their relation to mixing. I'm taking also the opportunity to tell you the little origin story for both this collaboration and kind of why we're all here today. It turned out that in 2022, on this island, we had this so-called symposium and advancing ocean observations. And I got invited to this. You see in the picture here that there's a couple other people you'll recognize, including Katarina and myself in the sort of top right corner. I have put a link to the paper that summarizes this workshop. The sort of key point maybe for today is that my idea for this workshop was to bring the so-called digital twin for ocean robots framework that is written in Julia. And based on that, in relation to that, I met with Jao, who's over there. And we sort of cooked up this idea of the Julia EO workshop that we have had the great chance that the Earth Center has decided to support it year after year after year. And that's how we are able to get engaged with all of you great people. And it's been a very fascinating chain of events for me. And so today when we are looking at Terceira becoming the Julia Island, in a way, it's this whole funny chain of events. The sort of things that I love about my job. It's like, you meet somebody here, and then you start a project there, and then you end up with something different. So anyway. The Digital Twin for Ocean Robots framework, I've already mentioned the name. I will have a presentation later to talk a lot more about the observational side. But essentially, it's the idea of bringing together models and observations in this kind of interactive way with enabling mutual benefits so that the models can learn from the data, and we can use the models also to guide the observational program and decide what observations we need. So there is a whole suite of observations that are built in there. One thing that is in the modeling lineup is these very high resolution simulations from MIT GCM. And so this is the movie that you were looking at a second ago, which I'm going to go back and play. I'm playing it for two reasons. One is that it speaks directly to the science that we want to do, right? So here you're looking at a variable, which is the gradient of sea surface height of the free surface of the model, and that is in this very high resolution model that has an external tide forcing, such that it generates global fields of internal tides. And so you see all of those beams that propagate across the Earth. Animating them makes your head kind of spin a little bit, right? There's a lot going on there. And so the fact is, there is all of this internal wave rated activity in the ocean that can have a very non-local impact on mixing. So it's a complicated topic to address. It's one where really you need these highly resolved and complex models. Another reason that I'm showing this is to highlight the fact that I would never have been able to do this without Mackie, the movie here specifically. And so this is something that, with a couple of caveats in the way I did it, such as the fact that the star background is fake, right? It's just random. I think there is some amazing opportunities that come to us from getting involved with Julia and with Mackie especially. And so this is my kind of showcase for that. So thanks for the community that is here and the community that's developing Mackie as well. All right. This movie, if you're interested, is available online. The .mov, I think, is available, and they're all listed on my web page, so you can go there and retrieve that. Okay. Just briefly about climate models jail, since we've been a little bit talking about it, it has relation to some of the other topics we've looked at today. So it's meant to provide a uniform interface to a whole host of climate models, or models in general, and one that is slightly different, I guess, than what Simone was talking about. Specifically, it targets maybe less interactive simulations. So the one that I just showed you, right, this ran over tens of thousands of cores for like a month and month. And as much as I like playing with models, I'm not going to keep my laptop looking at, turned on for 6 months. So it's the way we operate these models, typically once they get big enough, regardless of the language, is you dispatch them to a supercomputer or a GPU cluster or something, and you let it run. And then you come back to it. So this framework operates more in that fashion. It takes a model, provides a uniform interface to it that's simple and familiar to a lot of people, and then creates an instance of that, a folder for running the model, generating the output, and so on and so forth. And it includes Git as part of that workflow. So it's meant to be reproducibility enhancing. Here is the lineup that I have for now, and I'm looking forward to adding more. That's a suggestion to you if you're interested in this approach, especially. I think it's a good way to share your model configurations that have been maybe consolidated. I have one of those for Oceananigans, for example, that I'm going to show in a sec. But also, this is very flexible in the way that it integrates across languages and so on and so forth. So one of my goals, for example, is we have MIT GCM and Oceananigans, which are both great, similar numerics, different use case where one is better than the other. So for the simulation I just showed, MIT GCM is more ready. It's been done, and it's been widely successful with engaging scientists. But in many other cases, I want to use Oceananigans instead, right? Because it's faster, it's more tunable, it's more fun, and it runs on GPUs. So I want kind of a unified interface so that I can swap between one or the other, depending on the use case, essentially. So this is the roots of this climate models jail configuration. a comment on Oceanigans. I'm really looking forward to using it more. I have been sort of waiting for stability a little bit to be increased. And so this brings me to this slide that illustrates a point that I made earlier about the complexity that comes from the way that sometimes model development goes on in Julia, where we don't kind of have a very clear view on what the internal parameters are, where which text file is involved and all of this. And so when, in this example, I updated my configuration that I'm trying to curate and provide stably from 1 year ago to today, well, the results changed rather radically, as you see here. And so clearly I overlooked something. Now, very thankfully, this is fixed because Simone told me what the issue was last night. I rerun it this morning, and we're now good to go. So it's gives me an opportunity to first, thank the community for supporting me in helping me in that way in addressing the things that I overlook. Also, it gives me a chance to highlight that the huge success story that Oceanigans is and the promising future that it has. I'm convinced of this. But yet, to make the argument that I'm still debating to engage in my more kind of intensive exercises with it, whether I should wait for the version 1.0 or should I get going now? I'm still, this is one of the things that I don't think I'm the only user having that experience. So it's just, I thought it was fitting to discuss this here. With this being said, now I'm going to turn it over to George, to come over, who is going to tell you about the meat of the project and our goals. All right, thank you.
Oh, yeah. Oh,
Excuse me. So yours, where am I? Our next speaker is George McElghace. He graduated in oceanography from the University of Lisbon in 2005 and completed his PhD in internal waves at the University of Porto in 2012. His main research interest includes satellite imagery of processes with sea surface signatures, including internal waves, near-shore phenomena such as rip currents, river plumes, and fronts. Recently, his research has focused on software development for SAR and satellite elementary numerical ocean modeling, as well as high-resolution models for accurate representations of internal wave dynamics and their interactions with other physical and biochemical processes. I welcome George, sir.
All right, hi everybody. And before all, thank you so much, João, for the opportunity to be here. Thank you so much. So I guess the talk is a bit different in the sense that you guys are showing the state of the art of what you can do with Julia, and I've barely just began using Julia. So I guess the question on my mind was, how can Julia help me to solve the problems I want to solve? And those problems are related essentially to modeling internal solitary waves in the ocean. So a quick thank you to everybody that has, in a way, worked on the material we're about to see and the agencies that funded us. And although Adriana has already talked a little bit about it, I want to show you a little bit more about what an internal solitary wave is. So the family of internal waves is quite big. We will be talking about internal solitary waves. And I guess a picture might help. This picture is not mine, it's adapted. But I guess it shows pretty well what a solitary wave is, so you guys might just think of it as a surface wave flipped upside down and traveling inside the ocean. The scales, however, are pretty different, so the internal solitary waves can be quite big, especially in amplitude. So the amplitudes can go to the order of 100 meters, and the spatial scales can go to a few kilometers in the width of the soliton and a few hundred kilometers in the along crest length. The thing is that sometimes I get a little bit of trouble.
Tua apresentação não está a passar, portanto deve estar a fazer má conectação. Nós vimos aqui, mas no online não se vê. Deve estar a fazer má contacto. Tenta lá tirar de novo. Sorry. Foi o que aconteceu contigo. Tenta lá de novo.
E agora pôr?
Vamos fazer má contacto. Então vamos mudar por este. Espera aí. Tenta lá com este.
No worries, no worries.
Estás a usar? Consegues?
Man, this is easy to negotiate. No, not that good.
Deixa eu ver. Tá? Não, espera ainda, também não apareceu. Computador. Não é daí, não é daí. É da ligação dele. Se não faz mal, fazemos de outra maneira. Não? Pronto. Então fazemos de outra maneira. Fazes o filme. Ok, continua para ele. A gente arranja outra maneira.
Okay. All right. So sometimes I get in trouble because I will be showing you satellite pictures of internal waves, and for some reason, somehow people don't believe that you can see something underwater from space. So I just want to show you a movie that actually what we're seeing is the signatures of the waves. So I guess I hope you guys saw it. And trying to come a bit closer to the audience, because I know there's climate people here and so on, and ocean people, and try to make the case that they are interesting. Adriana has already showed that the algorithm that they have now to detect internal solitary waves is showing, and that was kind of known, that they are quite frequent in the ocean and they are in a lot of places. And by the way, we're going to have a meeting coming up this April about internal waves in Lisbon. Just in case any of you is interested, you can just talk to us. Where, by the way, there are a lot of internal solitary waves. And another thing I wanted to show you is that we've recently found that along the Pacific cold tongue, so I guess you guys have heard of El Nino, so this is kind of the opposite, it's La Nina. During La Nina you have this cold tongue spreading across the Pacific, and right at where the thermal gradients are stronger, you have direct generation of these waves. So they're not tidally generated as usual, they are generated by these currents and across these temperature gradients, which I guess represents almost a direct passage between very big scales and then through intermediate scales, which I guess is the internal solitary waves, and straight to turbulence. Because in fact, and this is just a zoom, so the island is right here. So it's that yellow thing, oh, it's here. So that's the island we're on. So the scales, as you can see, they're pretty big. This is Terceira. because what internal solitary waves what they really like to do is what they really like to do is to mix. Eventually, at some point, they're pretty good at advecting energy, transporting from somewhere to somewhere else, but along the way, and eventually, what they really do is they like to mix the water column. This is pretty well known. This is not ours. It's from Sam Havens, from the Newcastle University. But what we recently found out that kind of complements this is that internal solitary waves, they also fabricate, in a way, their own surface wave breaking. So although they're traveling underneath, on the surface, they increase the amount of surface wave breaking. So that means some kind of contribution, I guess, to this exchange between the ocean and the atmosphere. So to try to put that in perspective, the traditional view, when you put internal solitary waves alongside other ocean phenomena in this time space plots, I guess what this shows is that perhaps their area of influence is bigger than previously thought, in the sense that they extract energy from the larger scales and they tend to deposit that in the smaller scales. And me and Jose, we always come back to this analogy of Robin Hood, in the sense that they facilitate this energy transfer from the larger scales to the smaller scales. So that's kind of where we are or were. And again, satellite is really nice. You even get sometimes you even get a sense of motion if you use geostationary satellites. But the point is that we need more tools if we want to learn more. And a few years ago, we turned to modeling, and we turned to Martin Bausman, to whom we are very thankful. And he modeled using MIT GCM these waves in the Mascarene Ridge, which is in the middle of the Indian Ocean. There are some pretty powerful waves there, almost 200 meters in amplitude. And that clearly showed us that modeling was definitely the way to go. So we continued to pursue that, and we did a couple more works with MIT GCM, including off the west coast of Portugal, where we found out that actually internal solitary waves, they can play teamwork with wind. So if wind is blowing on the top of an internal solitary wave, what it will do is it will mix the water column much more effectively. And we modeled that with MIT GCM. The modeling results look ugly, but they're intentionally like that just to highlight the instabilities in the case that when comparing wind and no wind background stratifications. But unfortunately, about a couple of years ago, a year, 2 years ago, we lost basically the computer broke where we were running these simulations with Martin. So we were left without this precious tool that we were just beginning to understand and explore. Fortunately, however, João and the Air Center and Adriana, they facilitated the opportunity to install the model here in Azores and run it, and that's exactly what we are. So that's the point where we are right now, and with the goal in mind to go back to these waves in the Pacific and understand a little bit more about their energetics, because I think it's very interesting if you have a direct passage from a very big scale to turbulence even. We want to learn more about that, and that's part of a project we have with Gail. Gail already showed that. I'm showing it again. So that's ongoing. And going back to, I guess, the topic of the workshop, which is Julia. So I was completely new to Julia about until 2 weeks ago, and Gail kind of challenged me to do a couple of notebooks. And the most logical thing to do was, of course, with remote sensing, which is my background and in a sense what I still do. And with SWOT, so these two notebooks I will upload them to GitHub, and I kind of logged my thoughts and how I felt the code was, how the code was feeling to me. And thank you very much to the guys that developed all these packages for NC datasets and MIT GCM and Cairo and Maki. But I think the point is, it went reasonably well, and of course, like any coding language, you need time, right? So time will make it easier. So that's the one for satellite. This is the one to immediately take the binary data that comes out of the model and just have some diagnostic plots. That probably this is the one I'll be using the most. And of course, hearing about the shenanigans and seeing all the wonderful things it can do, and talking to you people, I guess, although the answer right now is no, maybe not use it right now. In the future, I'm pretty sure it's probably the only way to go. It's to use shenanigans. But I'll be happy to talk to you guys over the breaks a little bit more about it. So thank you. That's it. Thank you.
Thanks for this great talk, and I'm happy that you use also NC datasets. And you mentioned that you mentioned on the slide you couldn't download data directly from the internet. So I guess what you mean that you cannot use directly an URL inside NC datasets. That's what you wanted to do, and
I think I also realized they have an opened up. Maybe that's the way to go, I guess.
Yeah, exactly. Yeah. So if you have opened up, then it's the way to go exactly, because NC datasets directly integrates with opened up, and actually it's implemented in etcdf itself. It's not, and so you download exactly only the subset of the data that you need. Right. If you would you can also in Julia you can download a dataset just with the download command, but typically, this downloads everything, and it downloads everything every time you run the notebook. So typically, you would download it once and cache it. Right. But if you have opened up, that's definitely the way to go. Yeah.
Thanks.
So I wanted to follow up on that. Just a brief question. So I'm finding myself doing exactly that, to download as we speak, or I should say my postdoc is processing it all, the entire glorious quarter of a degree set of 3D fields. So we ended up writing, loops and bringing things by like month, and so some overhead essentially to using. I'm wondering, my question is there like a standard recipe to such a use case where you say, okay, this is a thread server in this case, open that, just get me the whole data collection and chunk it, put it to disk. The reason I'm doing that, of course, is because I want to then do computations on it, right? Is there like a recipe or an interest in kind of getting to that level of automation?
Any data set locally, but it does not do it quite intelligently with chunk. But since it's a PR of you implement it with disk array, that should be quite interesting.
I think the safecube data function in Azores would be able to do this. I mean, if it takes very long, we don't have basically checking yet. So we don't have breakpoints yet, but basically SafeCube takes the chunking into account, and basically you can load, and then you can. There's also ways to basically make multiple netcdf files into one disk array that it looks like one disk array, and then you can save it, and then you can set the chunking, and then you can, and then this will try. That's long. Yeah, I mean, it's. Yeah, we don't have checkpoints yet, so if it fails in the middle, that would be bad, I think.
Yeah, that's what I mean. But
Yeah.
So I guess I'm taking over the question session, but to you, George, first. I suppose you came from MATLAB in terms of your data analysis pipelines. How do you feel about Julia as a kind of a newcomer? I think it's a...
Well, after seeing all the talks you guys have shown and all these libraries and I think I have to do it, right? I mean, it's the future. I don't have a choice now.
Yeah.
Yeah, you guys had me at hello. Yeah.
We're sorry.
No, it's fine.
No, but it's awesome to hear.
I
right?
took the red pill or whatever,
Because
the blue pill.
bringing in people like yourself, I think is one of the things that I'm trying to do, and so I'm delighted to hear that.
Thank you, and yeah.
Maybe I can ask a quick question to Simone or to, I guess, the Oceanigans community in terms of, for this sort of configuration we're looking at to do internal waves, what's the readiness level of, or do you have examples already or something like this?
I think with respect to simulation,
Hã? Ah, sorry.
So I saw the simulations that you were doing were non-hydrostatic with a fully nonlinear free surface, right? So what we have right now is we have a non-hydrostatic model that works very, very well in boxes domain. In more complicated domains is a little bit slower because the speed of Oceanigans in non-hydrostatic framework is because of the pressure solver that is done in a very quick way. That is what is heavy in MIT GCM when it comes to non-hydrostatic modeling. We have a free surface in the non-hydrostatic model, but it's only linear. So I don't know how much the nonlinear part of the free surface matters in an internal gravity wave simulation, but that's something that we don't have at the moment. And when it comes to switching to Oceanigans, if you want, we are talking about releasing a version 1.0. So after that, the API should be stable.
Hi. So this is a slightly different question. You showed the visualization, the example of the internal waves in the geostationary satellite images. Is that something you have been working more with, or that you have some projects ongoing with, or was it an example from some other article?
Internal waves in satellite images.
Yeah, in the geostationary satellite images.
In geostationary, we used it, for instance, to take out phase velocities, which is a very important parameter. Not very often, but when there's nothing else, we look in geostationary satellites, and they're not always very visible on them. You need the good sun glint conditions and so on. Actually, that particular region of the ocean, off the Amazon shelf, that's, to my knowledge, that's actually the only place where geostationary satellites can see them well enough. Yeah. So, thank you.